In this video, we will mention some of the properties of the dimension of a vector space. We already have shown that if we have a vector space and we know that B1 up to Bn is a basis, that means that these vectors are linearly independent and every vector in W can be written as a linear combination of these. Then if we have some other vectors, W1, Wm, and m is greater than n, then this set, let's call this set D, D is linearly dependent. As a consequence of this theorem, we know that every basis of the same vector space must have the same number of elements, which is called the dimension of the vector space. Let me mention another theorem that is easy to prove. If we have some vectors B1 and Bk, and let's suppose that they are linearly independent. They are not necessarily a basis, but they are some vectors linearly independent in W. Then it is easy to prove that if W, a vector in W, is not in the span of this set, let's call this set D, in the span of D, which is denoted like this, then these vectors B1, Bk, and W are linearly independent. The proof of this is relatively easy. We assume a linear combination that produces the zero vector. Equal to the zero vector, and then we need to prove that all the alphas must be zero. First condition, if in the case that alpha k plus 1 is equal to 0, then we get that this linear combination must be 0, but since these vectors b1, b2 up to bk are linearly independent, then we conclude that the alpha 1 up to alpha k are also equal to 0. And if this happens, then alpha 1 equals to alpha k equals 0. Now, if alpha k plus 1 is different from 0, then we get that this is not possible. Because if this is possible, that means that W is equal to negative alpha 1 over alpha k plus 1 b sub 1 plus negative alpha k over alpha k plus 1 b sub k, and we are assuming that W is not in the span. Then this is impossible to happen, and if this is equal to 0, then all others are equal to 0. That means that these vectors are linearly independent. Another property that we can show is the following. If we have some vectors, let's say B1 up to Bk, then from this collection of vectors, we can pick a subcollection, let's call it D bar equal to B sub E sub 1, B sub E sub L. We pick some of them such that the span of D bar is equal to the span of D, and D bar is a set that is linearly independent. How do we show that? We start selecting the first vector. If B1 is different, is not 0, then we just pick B1. Then we check if B2 is a multiple of B1. If it is not, we include B2. If it is, we just remove it. And then we check if B3 is a linear combination of the previous two, and if it is, we remove it. If it is not, we include it, and then we keep with this process until we get a collection that spans the same set and they are linearly independent. Notice that we are using this previous result. And as a consequence of these theorems, we have the following. We have that if the dimension of a vector space is n, and we have a collection of vectors v1, vm, and m is smaller than n, then necessarily the span of these vectors v1, vm is not equal to w. W is going to be bigger than this span. And the reason is that from this collection of vectors, we can take a collection of some vectors here. Let's call them v is 1, v is k, with k smaller than m, smaller or equal, such that these are linearly independent. But these are linearly independent, and if the span of this subspace is the whole W, that means that the span of this subspace is the whole W, and they are linearly independent, and therefore we will get a basis for W with k elements, where k is smaller than n, which is a contradiction. For that reason, if we have a collection of vectors, and the number of those vectors is smaller than the dimension of n, therefore those vectors are not enough to generate the whole space. What other property we have? If we have n vectors and they are linearly independent and the dimension of W is n, then these vectors must span the whole W. And the proof is easy. If they do not span the whole W, then I can pick a W that is not in the span of these vectors. But if I pick such a W, we already showed that if they are linearly independent and we select a vector that is not in the span, then we will get that this collection of vectors are linearly independent. But this is impossible because we know that the dimension of W is n. That means that we can pick a basis. Let's call it W1, Wn, a basis for W, and this set it has more elements than n, therefore they must be linearly dependent. Then, as a consequence, if we want to prove that some vectors form a basis for a vector space, and we know that we have the right amount, if we have n vectors, and then it is enough to show that they are linearly independent, because if they are linearly independent, they must span the whole W. Let me just show you an example of this. Let's think about P2, polynomials of degree 2 or less. Example, we know that a basis for this set is the polynomials 1x, x squared, and it is easy to prove that the polynomials 1 plus x, 1 minus x, 2 plus x squared, it is easy to show that they are linearly independent. Therefore, since they are linearly independent, then they must be a basis for P2, because we have the right amount, they must span the whole W. Then they are also a basis for P2, because the dimension of P2 is 3. Then this is an application of this theorem. We also have that if the dimension of W is n, and somehow we have n vectors that expand the whole vector space, then these vectors must be linearly independent. Then let's say B1, Bn must be linearly independent. And the reason is that if they are not linearly independent, we can take a subcollection of vectors B is sub 1, B is sub k, with k strictly smaller than n. If we assume that they are linearly dependent, then we can take a subcollection of vectors from here such that this span the same set, span the whole W, and they are linearly independent. But this is a contradiction because these vectors would be linearly independent and the span is also W. That means that these bases will have a smaller number of elements as the dimension of W. Therefore, if we know that some vectors, if we know that the dimension of a vector space is n, and we know that some vectors span the whole space, necessarily they must be linearly independent. Let me show you another example. Then the matrix is 2 by 2, right? This is a vector space of dimension 4. Here is a basis 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 1. And then we are completely sure that these matrices 2, 1, 1, 1, 3, 1, negative 2, 4, and 2, 1, 7, 2, the span of these three matrices is not M2 by 2. That means that we can find a matrix 2 by 2 such that cannot be generated by these three matrices. Why? Because three vectors in a four-dimensional space, they cannot span the whole vector space.